Okay, hi everyone. Welcome to our 11:30 press conference. This is explaining extreme events in 2015 from a climate perspective. Our participants today are Jeff Rosenfeld, Stephanie Herring, Martin Herling, and Freddie Otto. Take it away.
Hi, I'm Jeff Rosenfeld, Editor-in-Chief of the Bulletin of the American Meteorological Society. We're very pleased to present these findings in our journal as a special edition. It's the 5th year, actually, that we've been explaining extreme events. And it's the first year in which climate change has had to share the spotlight with a major El Nino event. This climate, sort of double jeopardy, as you might want to call it, presented a worthy scientific challenge. Just as importantly, it served as an opportunity to showcase the growing value of climate attribution studies. And that's really what this volume is all about. It's a showcase. So to appreciate this moment and this double jeopardy moment, let's go back to 1997-98. That was an El Nino year, much anticipated because the previous big event in 1982-83 had caught scientists pretty much flat-footed. At the fall AGU meeting in 82, researchers were talking about volcanoes and how an eruption had caused warming in the Pacific. Half a year later, they were calling it El Nino, and a lot of scientists at that point didn't even know the word. By 1997, though, scientists were ready for El Nino, but they were not ready for the media. Different problem. El Nino went viral. It became a household word. Then it kind of became the butt of jokes, right? People were talking about blame it on El Nino. In fact, blame it on El Nino became a popular song. El Nino took the blame for all kinds of weather. It took the blame for droughts and deluges, heat, cold. It also took the blame for all sorts of things like civil wars in Africa, the fall of the Incas. Worse yet, there was a failure to communicate coherently then what El Nino was affecting. And this, in turn, affected talk about climate change. The public could see that anthropogenic climate change was also blamed for a bewildering variety of phenomena, just like El Nino. Of course, climate change is even more pervasive than El Nino. So we look at climate change and we wonder, did humans cause this? People are asking. This topic comes up whenever something strange happens, like an extreme event. For years, in response, it was safe to relate climate change to current events, but only in the most anodyne terms. This was clearly unsatisfactory both for scientists and for the public. It just wasn't good enough to talk about climate change, this gradual phenomenon. People deal with extremes. They talk about, they realize they live with the bumps in the road, not the gradual changes in means. They live with storms and droughts. Scientists, though, knew there had to be some way of relating anthropogenic climate change to what's going on now, to present-day extremes, to what people are actually experiencing. And they could do it without repeating the fiasco of 97-98. They came up with new ways to communicate, and those new ways are here in this volume. I think that's why it's so important. In just 5 short years of collecting these papers, we're starting to see more confidence. We're seeing researchers asking better attribution questions, and we're seeing them answer them with better tools. They're now able to ask questions that the public is asking, like, is this the new normal? And is it the new normal here, right here, not globally, but right here where I live? Now that attribution is so much more urgent for people, it's amazing and wonderful to see that attribution science is achieving a new success. A new scientific field is being born. And fostering that community is the point of publishing these papers. This is historically what the Bulletin does. We brought peer review into this, and it's essential to the process because not only does it ensure rigor, but it broadcasts the new developments and coalesces a field and a community of people. We've engaged well over 100 experts to independently review these papers, and this exposes a large swath of the climate community to these issues, to the kinds of tools that are available, and to the findings. And because explaining extreme events is an extensive community effort, it serves more effectively that way as a proving ground for these new terms of climate change communication. It brings together specialists with the wider scientific community, and it encourages new applications as well as public discussion. And that, of course, is our mission as a journal. The bulk of the credit, of course, goes to Stephanie Herring and to her team of editors. And they basically, what they've done here, not only are they coaching their peers in new terms of communication, but they've collected a lot of papers, encouraged a lot of people to contribute. They've innovated a new format. All of these things are very important. We also have to thank the authors, of course. They actually succeeded in doing what they were asked, which is tremendous. And I think it's important also to thank those reviewers, those hundreds of people who have been looking at these papers and pushing us to do better and better. So explaining extreme events, it's a demonstration of capabilities, and it's fitting, I think, that in this 5th edition, as you're going to hear in these fascinating papers, really, that it was a stiff challenge, and they met it, to untangle the effects of El Nino and anthropogenic climate change in a year full of incredible extremes. Such papers would not have been possible not long ago. So since old habits die hard, I guess I'll just say that that's something we can blame on El Nino. Stephanie?
So, thank you, Jeff. My name is Stephanie Herring. I'm with NOAA's National Centers for Environmental Information, and I'm the lead editor of the BAM's Explaining Extreme Events reports. I'd also just like to, for everyone's awareness, that people know that we have a lot of authors from the different chapters in the room. So if you guys don't mind just raising your hands really quickly to show where they are. Great. So if you do want to have any follow-up questions or interviews about specific papers, we encourage you to find an author and ask them about their paper. As Jeff mentioned, this is our 5th year of publishing this supplement. And I wanted to start with very, very quickly, just reviewing again, what is attribution research and why do we do this? So attribution research is the process of assigning, or attribution itself is the process of assigning a cause or a reason to something. And in this case, it's extreme events. So what these papers are doing is they're looking at the various physical drivers that cause extremes, El Niños, sea surface temperatures, blocking patterns, atmospheric circulation, wind patterns, et cetera. And in addition, looking at whether human-caused climate change changed the severity, the intensity, or the frequency of the extreme event they're looking at. And why do we do this? Well, we do this for the same reason we've always tried to understand our weather. And that is because we know that if we can better understand why these events are happening, we can better predict and prepare for them in the future. And so these papers are really about providing information to people like you and me, like governments, like businesses, to understand how their exposure risk to extreme events is changing so they can use that information and plan accordingly. So what did we see in this year's report? We had 25 peer-reviewed research papers here looking at actual extreme event attribution, and they covered 5 continents and 2 oceans. For the most part, we had the typical heat, precipitation, drought papers that we've seen in the past. This year, we also had some fun new ones, including extreme sunshine, a snowpack drought, and a sunny day flooding event. So a couple, just briefly, some U.S. event highlights. For the risk of flooding during high tides, during otherwise completely sunny days in coastal Miami, this is actually our cover photo this year. A blue sky day, but you also see flooding. This type of event has increased significantly because of human-caused climate change, whereas in contrast, the eastern U.S. cold winter, which we experienced in 2015, was found not to be linked to climate change. 2 other events, the snowpack drought in Pacific Northwest had exceedingly high temperatures, which led to their overall reduction in snowpack, which was related in part to human-caused warming. And the Alaska wildfire was the 2nd most extreme fire season since record-keeping began in 1940, and this was also found to likely have been linked to climate change. Globally, a couple highlights were the heat waves around the world, and we've seen this again and again over the years, were made more intense by human-caused climate change, and climate change contributed to making 2015 our warmest year on record. On a bright note, extreme winter sunshine in the UK has actually become 1.5 times more likely because of climate change. But in contrast, perhaps not such good news, extreme cyclone activity in the North Pacific is also becoming more likely because of climate change. So after 5 years, where are we? We've now published over 104 papers, and I definitely want to emphasize this is not a random sampling of events from around the world. They have selection bias. Our authors choose the events that they look at, and our authors tend to be like you and me. They care about the events that happen close to them. So for the most part, There tends to be, the author groups that look at events tend to actually be from those regions and personally maybe have experienced the extreme events they're looking at. For the most part, we get heat, precip, and drought are by far the most dominant papers that we get. And as you'll see, one of the things that we've seen over the last 5 years is that this report contributes to the overwhelming scientific consensus that, first of all, extreme events are being influenced by climate change today. And second of all, that the clearest and most strongest line of evidence is that it's having an influence in particular on heat events. When we look at events such as precipitation and drought, however, and other event types, whether or not a climate change signal is found is decidedly more divided. And in fact, for the precipitation papers, over half do not find a climate change signal. For the report as a whole, over the past 5 years, about 35% of our papers have not found any role for climate change in the events that they've looked at. And we actually really welcome these papers because we find that papers that don't find a signal also provide us with incredibly valuable information. One, they tell us where our risk is and is not changing because of climate change. But the other part of it is they certainly tell us where we need to be able to advance our understanding in the research area in general. But what do we mean when we say that papers don't find a climate change signal? And there's actually many reasons why this conclusion can be reached. One is simply that it's not possible to measure the human influence of climate change on the event, and that's the most straightforward answer. But the other is that, as I mentioned, there's a variety of physical drivers that play into creating any extreme event, whether it be El Niños or sea surface temperatures, et cetera. And it's possible that a particular paper only looked at a subset of those physical drivers. And so we don't actually have the complete story yet. And finally, it could be that the human influence is simply not able to be detected with the scientific tools that we have today. So the 3 pillars of sound attribution include our ability to have a strong observational record, the quality of the models and their ability to reproduce the events, and our understanding of the physical processes that drive these events and how climate change might interplay with those. And so in the absence of those, it's possible that the tools that we need simply aren't available right now. And in all cases, because these tools are so important, as models, data analysis methods improve, future studies can absolutely yield new information. And so with that, I will turn it over to my colleague, Marty Horling.
Well, welcome everyone for our 5th report. Go this way. And I want to give you a little sense about what this report does and doesn't do. One thing it doesn't do is cover all of the extremes that did occur in 2015. I think our report has, 25 uniquely distinct events. You could increase probably by an order of magnitude the number of extreme weather phenomena that occurred, just as a rough estimate, during the course of 2015. So I think it's important to keep this in mind. The events also that were chosen, as Stephanie said, were not a random selection. Scientists are interested in things that happen in their backyard. They have resources and they have the willingness and the team in place to go ahead and attack it. Nor are all the studies that have been done on extremes appearing only in this BAMS issue. You'll find other publications, people who really put teams together and did rapid assessments of events in the literature elsewhere. So this is a subset but a significant sample of events that were studied. Most of these events were not foreseen by the scientists. So these happened after the fact. They caught people's attention. They made good sense for study for obvious reasons of societal impact. We'll hear more about that. And the other important point to remember in this regard is that there are a variety of unexamined events, and I'm going to touch on that in a second when you look at a global context. And so we don't want to think there's only 25 extremes that happened in 2015, but rather that there are numerous areas that experience extremes, but that were simply not in the venue of this analysis. So 2 papers were done in this report that looked at a global context. One on temperature, I'll share that first, from GFDL scientists led by Cam. And I think if you focus just on the top slide on the right, and I'll explain what is being shown there, it's really a rather remarkable slide. And it concerns annual temperature extremes, and it looks at a data set, an observational data set, in which there are complete measurements over the globe, at each point over the globe that go back 100 years, I think to 1901 or so. And what it's showing is a time series of the percent of area in which there are observations that had the hottest, second hottest, or third hottest year in 2015. And I think you can see, if I can use a pointer to help draw your eye to it, we are just way off the chart. About 30% of the portion of the world that had observations of 100-year or so duration recorded the hottest annual condition on record. And this eclipses all prior years by a significant amount, and you can see the time series is just spiking up. So we are in a warmer world that's warming rather rapidly, is what this is telling us. The blue curve says the number of locations over the monitored world that had record low temperatures or ranking in the top 3 coldest years, and I believe that is probably effectively 0, I think, maybe very close to 0, if not 0. This is the world that these events are occurring in. And if you look at the map below it, you'll find the locations where many of our case studies were selected. There's European heat waves that were studied, South Africa heat wave that was studied, Northwest Asia heat wave that was studied, but some that were not studied. For instance, Southern California, and the state of California as a whole was one of the warmest years on record. I don't believe we have a paper on that in this report. Also, the oceans were particularly warm off of the California coast, off of the Atlantic seaboard into the Indian Ocean. And I don't believe we have any particular studies on hot oceans, if you will, heat waves in ocean surface temperatures. And those are very important to address because it's the thermostat that drives the land temperature coming from the oceans. And so we don't have that in this report, but maybe in the future we'll see more of that. Precipitation is, I want to go back and just really say one other thing. The white areas in this have no data that is of 100-year duration. It's very important to keep in mind that we're not sampling the world as completely as we'd like in a long historical context. And so that challenges us. It's not that there wasn't Arctic warming, for instance. In fact, there's a significant line of evidence that the Arctic was close to, if not the warmest year on record, from other data or data of shorter duration in which we can place the Arctic 2015 case into context. So don't be fooled by the absence of information here. If you will, the dog was barking in the night. We just didn't have the data to hear quite what the dog was saying. Precipitation is another challenge for us. We would love to place a global context for extreme daily precipitation, but we're challenged to do that in the time scale of these types of reports. The U.S. provides one of the better, as does continental Europe, data of daily precipitation. It goes back 100 years, about 900 stations. Here you're seeing a network of daily precipitation stations that has a duration of 900 years. This is based on one of the papers in a report from University of Colorado scientists coming out of Sirius, a cooperative institute that works with NOAA. So about 900 stations, and then below here are the stations that experienced at least one in 20-year event, an event that you wouldn't expect to happen, but one every 20 years, pretty rare event. And then the time series is also striking because it shows the percent of stations that experienced 1 in 20-year events from 1900 up to 2015. 2015 wasn't extreme, but it ranked among the top. In fact, 9 of the 10 most extensive occurrences of 1 in 20-year rainstorms have all happened since 1990. A lot of numbers there. The point being is that we are ramping up the frequency of heavy rain events over the continental United States. There were, I don't believe, Stephanie, any papers in this report on heavy rain events in the U.S. And there was a very noteworthy one about a year ago in the St. Louis, Mississippi Valley, central U.S. in November, December. And it was a remarkable event. It stood up and above all prior wet day occurrences in that region for that time of year. We did not get a study on that. It's one we might want to come back to. If you pay closer attention to the general scientific literature, I'm sure something will come up on that case. So that's just giving you a sample. You can see how sparse some of the data are in the West and how dense it is in the middle of the country. And so we have to deal with these inhomogeneities. And so with that, I think I'd like to bring up Freddie, who's going to touch on some of the impacts in a global context with the next slide.
Yeah, hi, I'm Freddie Otto from Oxford University, and I'm the only one who's not an editor on this panel, but author. I think I've been an author and co-author at least in every one of the 5 years so far. I would like to sort of talk about a bit what the next really big challenge in extreme event attribution is. I think the 5 years of this report from BAMS has shown that we have made enormous progress in terms of attributing the meteorological events, so extreme events from a meteorological point of view. However, what most people who are asking the question, was this due to climate change, are actually asking is looking at the impacts of these meteorological events and not for the meteorological events per se. And so I think this is really the next big step that the attribution community will have to do, and which we can't do on our own, but where we need to link with the other communities that work on impacts, with hydrologists, with health, people, health workers, water management, perhaps. But we see in this report some steps into this direction. But first I would like to do one step back. Sort of, we don't really know what the impacts of anthropogenic climate change are today, independent of extreme events. There are not many studies that really make the step from an impact to anthropogenic climate change. And here is one paper which has been published last year that has nothing to do with BAMS, but that tried to put all the evidence from impact attribution together that we have for impacts of anthropogenic climate change. And you can see so here's an impact on fisheries that is from long-term trends in ocean temperatures, or here this is the water availability from glacier melting in the Himalayas, so also something that is a very long-term trend. But what is completely missing on this overview slide is the impacts from extreme weather events. And when we just look at the year 2015, so this is an overview map of the record-breaking events in 2015 alone that were reported by the WMO. And we can see, which sort of matches with the maps that Stephanie and Marty have shown, there are a lot of heat waves, and some of these heat waves are actually tackled in the report. But there are also a lot of other events where we don't know whether and to what extent anthropogenic climate change played a role in these. However, what we know is that in the short term, the largest impacts, and in particular the highest damages of anthropogenic climate change, are presumably through extreme events. And if we really want to put numbers into this, then we need to work with impact modelers and with the impact community, and to see how we can make the link from the meteorological events to the impacts. This is not necessarily straightforward, but there are ways to do that, and we have seen in the last few years some papers on that, and we do see some in this report. So, for example, if we have a flood, then we can look at the extreme rainfall that led to this flood. But it makes a huge difference in terms of whether or not there would be a flood if we look at the one-day extreme precipitation, or if we look at a very wet season and then a one-day extreme precipitation. So from the definition of the event and from the way we frame our study, this is a very different question to ask. And only one of them is really linked to the impact that we've seen on the ground. And of course, flooding is not just dependent on the rainfall, but also on the size of the river catchment, on the management of the catchment. And in last year's report, we saw one paper for a Canadian flood that has actually looked into this event. And the same is true for heat waves. So we can look at the temperature in heat waves, and a lot of studies have so far in the past focused on the temperature. However, what, for example, affects the human body is not the temperature as such, but is the heat stress, so a combination of temperature and relative humidity. And when we look in this year's report, so there are two studies on the heat wave in Europe in 2015, and we can. And one of this study by Dong et al., so they have looked at this region. They looked at temperature. They also looked at precipitation anomalies. And then the other paper by Sebastian Sippel et al., they looked at the heat stress and the temperature, and just to see what the difference is. So we have seen in other studies that in some events you see a huge impact of anthropogenic climate change on the heat wave in terms of temperature. But the impact is much smaller on the heat stress. In this case, we see a different picture where actually the temperature increase and the heat stress increase is quite similar. But this really depends on the kind of heat wave and on the kind of the region the heat wave is happening in. And another study in this report is looking at that heat wave in Egypt, where there also the heat stress is looked at and not just the temperature. So that is, in this report, there are some examples of really making the link between the meteorological event and the impacts. And one last point, of course, it's not just the impacts in terms of relating hydrological and meteorological variables, but whether or not an extreme weather event leads to large impacts depends on vulnerability and exposure. So in the last year's report, we looked, for example, at a drought in Sao Paulo and found that there was no detectable influence of anthropogenic climate change on the drought in terms of a meteorological event. But we worked with water management people from the area and also looked at population increase and found that, in particular, there was an exponential increase in water usage in the last 10 years in that region. So the meteorological event was a 1 in 10 year drought, and it has been a 1 in 10 year drought even in the world without climate change. But because other human factors have changed dramatically, the impacts were much larger. And only with all this information together, we can really paint the full picture of what is the human influence on extreme events and their impacts. Thank you.
Okay, so now we'll open the floor to questions. Are there any questions from reporters in the audience? Do we have any questions on the web chat?
We have a couple questions from Seth Borenstein from the Associated Press. Seth asks, regarding the Northeast cold snap, could you please explain why you don't think that it counts as influenced by anthropogenic global warming?
I'll go ahead and take that on. There are two papers in this report on the Northeast U.S. cold winter. And the main findings were that the extreme coldness that occurred either on a cold snap, like a week-long time scale or daily weather time scale, and even on a monthly average time scale, were not made more likely by anthropogenic climate change. Now, the way I understood Seth's question, it seemed as though he was saying, well, this was not a climate change-induced phenomena. Indeed, I guess the moral of those two studies is that climate change is not making winters more extremely cold, either on weather time scales or on monthly time scales. That the evidence in the two studies, which were different lines of evidence that were applied to that very same question, came up with the same conclusion, that actually climate change is making temperature in winter less variable on a daily time scale and making it warmer on average on a monthly and seasonal time scale. So that cold waves, cold extremes, the polar vortex, and phenomena of that type that were quite popular in the public discourse are not a consequence of climate change. So those two studies help clarify that debate.
Okay, go ahead.
Another question from Seth. Seth asks, in Chapter 26 regarding the cyclone in the western North Pacific, which typhoons or cyclones are we talking about, and which would be good examples?
Sounds like Jeopardy. I'll take column 26 for, let's see if we can dig that one up real quick here.
To clarify on that paper, they actually looked at accumulated cyclone energy across the region. And I actually believe one of the authors may be in the room. They currently have their hands up. So if that's a follow-up question for anyone in the room, but I would defer to them. They did not look at a specific cyclone. Accumulated cyclone energy was a calculation of all the different cyclones that happened over that particular region over a period of time.
Maybe I'll just read their encapsulation of their main finding. Zhang was the lead author of that paper. And they stated extreme typhoon energy over the region of the western North Pacific during 2015 was mainly the result of El Nino-related sea surface warming of the tropical East Pacific. What they mean is that El Nino tends to relate to tropical typhoon activity in the western Pacific, and it did so in 2015. But they go on and say, though the effect of human-induced ocean warming also made such an active season more likely. So two factors were at play that they identified, one that we know fairly well and one that's emerging in the context of how we understand a changing climate to be affecting weather.
Okay, what else? Okay, do we have any other questions? Go ahead.
We have a question from Tom Henry at the Toledo Blade. 26 regarding the, what is the applicability of this research to the Great Lakes region?
I would say that we actually have we had an event in the past reports that looked at that region? We've certainly had Midwestern studies. So I think that, when the applicability of this field as a whole is that when extreme events happen, regardless of where you are in the world, whether it's the Great Lakes or Southeast Asia, that this field of attribution science is able to now come in and look at and try and understand what was the event that happened, what were the natural drivers that would cause this event to happen. In addition, is climate change playing a role in your region to make this type of event more intense or more frequent, or perhaps changing the geographic location of these types of events in a way that impacts you? And that, I think, is applicable regardless of where you are in the world, not just the Great Lakes region.
Maybe to add, if I could, Stephanie, a couple of, and these weren't addressed in this, but they appear in other assessment reports that have been done by the National Academy and National Climate Assessment. For instance, take one example, maybe a simple one. A lake level is very important for a variety of reasons, fish navigation and so forth. So if precipitation is changing in a particular direction, I'm not saying that it is in this question, it's hypothetical, the lakes are very sensitive in their elevation. That affects commerce in particular and the health of the ecosystem. Algae bloom would be another one. Unusually warm temperatures, poor dilution if the precipitation is low. All of these are important for the health of the ecosystems. And the other one is not widely appreciated, but a warmer climate, as we are experiencing, leaves those lake surfaces open later into the winter. And it seems counterintuitive, but for those that have lived along and adjacent to the lakes, I live near Milwaukee, lake effect snows are beautiful things to behold, but boy, do they cause a nuisance. And you would think in a warmer world it'd be less snow, but actually the lakes being open later, cold air eventually does find its way during the course of the winter over those late opened lakes, produces very significant lake effect snows. Is there a trend to that? I don't know. Others will be speaking to that hopefully in the future, but that's just 3 examples come to my mind.
Okay, do we have any other questions?
Hi, Scott Waldman with Climate Wire. Is it that the research has improved in the last 5 years that you've been doing this study, or is it that the evidence of these extreme events in just 5 years has grown to point towards more of a human influence?
I think what mainly has grown is the research and the research capabilities. So first of all, the development of attribution methodologies, and that we now have several different independent methodologies that we can apply, and so also assess the confidence we have in the results. And then also just the fact that more and more scientists work on this and can make the data sets they have access to available, which is sort of one of the main barriers in event attribution studies. If we don't have the observational data sets available, then we don't know what happened, and we cannot make an attribution study that is really tied to the event. So that fact as well to the methodological development has led to much, much better attribution studies now.
The other thing that I'll add to that is that another paper that came out, I believe it was this year, actually did a retrospective, taking attribution methodologies and looking back over the course of, I can't remember the exact time frame off the top, but several decades, and things that things that have happened long ago, where we didn't actually have the quality of the models that we have today, and our ability to pull these data sets together and pull these observational data sets together didn't exist at the time of these events. Attribution didn't exist at the time of these events. And when they went back and looked at them, they actually found a significant proportion of these heat events having a climate change signal decades ago. And that, I think, was also a very interesting result, is that, and when you think about where we'll be in several decades and people coming back and looking at the events that we have today, what are we missing because we don't have the scientific tools today? And that, I think, is an important question for us that will, hopefully scientists that will be around in 20, 30 years will come back and look at some of these events again with the new tools and new observational data sets and new modeling capability and our new understanding of the physical processes, and provide us with even a better understanding, much like this paper did for events that happened 20, 30 years ago.
Just a little bit more color, because the history is really neat in this. 2003, the European heat wave. 2004, colleagues from Freddie's that she works with, Peter Stott was the lead author, did a paper on the European heat wave. It was published, I believe, in Nature. Probably the first study to really apply statistical formalism with model capabilities at that time that were available. Have heat waves become more often now, or have the methods gotten better? And so that's really what's... Heat waves have become more common, and that is what we call detection. So it's becoming more evident to the even almost the untrained eye that we are living in hotter summers. And this has especially been true, I think, in Europe more so than in the central part of the U.S. for reasons we don't entirely understand. But in some parts of the world, heat waves are becoming remarkably common. Now, what does this mean? It means actually that all boats are rising with the tide. In summer, the tide is fairly low, and increasing those temperatures by about 1 degree makes that exceedance above the tide very noticeable, especially if you're not adapted to much temperatures above that. This is especially becoming true in the tropics. And so there are impacts also coming back to impacts that are beginning to be felt whose attribution hasn't yet been solved, but that is the huge spike in chronic kidney disease in Mesoamerica, related in part to heat stress and other practices. And so this is all becoming part of a warming world that is becoming more detectably warm, and now the impact is what we're really interested to sort out.
To add just a meta-scientific comment, I guess, if that's right. I think some of the basic papers in this field seem to have been published in the late 90s in terms of techniques and statistical ways of looking at this, and also after the European heat wave, a real big landmark in terms of the field. So it's really interesting just to look at the references and see how young the field is. The other thing is that when we started, we had maybe 10 events, 5 or 10 events in one, 6, it was 6. It was a very small operation, but I'll tell you, it was kind of hard finding reviewers just for a small project like that. A lot of people weren't familiar with the techniques, they weren't familiar with the kinds of questions that could be asked, and how to use the models and other tools to address the questions. And so I just see in 5 years the growth in the number of people I can ask who will say, yeah, I can take that on as a review question. That to me tells me that people are becoming more comfortable with the questions and the tools, and they're starting to adopt a common language about how to express the risk of an extreme event in a way that makes it possible to start doing more studies and feel comfortable that you've got the right approach. So the other thing with this project is to do this quickly. This is sort of a fast response kind of science now, because people ask a question about a heat wave, they want to know now, is this climate change or not? And so there are people now branching out from what we're doing here and trying to do it outside the peer review system and crank out quick studies that provide answers. And I don't think they'd be emboldened to do that if there wasn't sort of a set of tools that everyone had kind of agreed on through peer review. So in a way, we're continuing to try and innovate those tools in this edition that will hopefully help spread good quality science to these more operational time frames for people who are trying to answer these questions now, for policymakers who need to know answers now.
Just to keep going on this, because it's so much fun, it's a great question, opens up all kinds of conversation. The rapid timescales. One thing we are learning is there are certain needs for information. There are certain needs for science. We want to forecast these kinds of events better. That takes a while to assess how well we can anticipate the events that we're diagnosing. But then there's a conversation that is very rapid that comes out right the day after an event is happening. It's like, geez, what do you make of that? I mean, have they ever seen anything like that before? Is that the climate change of which you speak in these big reports? And then sometimes you address that by, well, here's 50 years of data, and no, this has never happened before, so it must be climate change. That's, of course, a very naive statement. We try to avoid that at all costs, but it may actually be also true. So to be naive on the other side would be to deny the possibility that even though I've never seen an event like this, and there's no trend in such a statistic, that climate change isn't affecting its likelihood today, because the very nature of the rareness of these events means you could have gone for a stretch of 50 or 100 years. Look at the 1930s Dust Bowl. In some places in the U.S., we haven't exceeded the 1930s Dust Bowl, and people say, well, that means there's not a warming trend in the U.S. There's no climate change operating on U.S. temperatures in the Corn Belt during the growing season. That's patently false as an underlying science, even though it's true that we haven't exceeded the 1930s Dust Bowl heat. So these are important narratives to be able to balance out and communicate. Some of them can be done rather quickly, but often you get a naive one-side perspective. In these reports, which are taking a year or so to process, hopefully it's a little bit more measured, if not as timely as I know some would like to have the information.
But to add to that, I think also exactly because these naive views always come up, that when we are doing the rapid ones where we come up with scientific results 2 weeks or so after the event, the important thing that we are doing there is we use the peer-reviewed methodologies in exactly the same way as we apply them in the peer-reviewed papers to exactly be able to disentangle what is something that is just, okay, what we expect from the overall warming effect. We expect heat waves to become more frequent, but climate change also can have an influence on the atmospheric circulation. And when you look at the overall likelihood of the event and whether or not that is increasing, you need to take both into account, which is why we need these attribution methodologies and cannot just look at the trend that we see in the observations. And I think with having these peer-reviewed papers and peer-reviewed methodologies, we are able to apply them in a shorter time frame after the event, when people are really asking the question, what is the role of climate change?
And also, these are really tricky kinds of questions. That's why I feel like you wouldn't have even asked these kinds of questions 20 years ago, because they're not just looking for, did climate change have an effect? It's anthropogenic climate change. That's a very refined question to ask. So it's very impressive to see what's done with those kinds of questions now.
Okay, I believe we have a question from the chat.
Another question from Tom Henry. Tom is curious about the argument that we can't rely so heavily on past climate trends because we're entering uncharted territory. He wonders if you could address that idea. He asks specifically, do you think there's too much reliance on rainfall statistics in the last 50 years, especially when trends are changing so quickly?
I'll start with that, and then you'll rescue me from the deep hole I will inevitably dig myself into on this. NOAA has an atlas that is very important in the user context. It's the Atlas of Extreme Daily Rainfall, which is used by municipal managers in flood planning, urban drainage planning. These are the statistics based on where 100 years of data exists, if not 50 years of data. I think the minimum requirement is 30 years of data, but it's retrospectively looking, and it asks what is the likelihood of a 1 in 100 year event, and what's the magnitude of that on a daily rainfall at all points in the U.S. that exists through time. And some are beginning to ask, so the Louisiana flood is a classic example of the complexity of this. The Louisiana flood that occurred just a few months ago exceeded prior record values. And the question is, was that I'm just going to toss a number out here, a 1 in 300 year event consistent with the expected return period of data that was 100 years old? Or is it now a 1 in 100 year event consistent with the near future and going forward? So these are really important questions for engineers. So when Stephanie asks, why do we do attribution? We want to know whether the return period is something that has a devastating effect on infrastructure and society, that it may cost a complete rebuild of a community and its water treatment plant or its drainage system. Big costs, big ticket items, big economic consequences. We want to know if that where we had assumed was a 1 in 100 year event is now a 1 in 50 or a 1 in 20 year event. It's critical that we figure that out. And those are thorny but critically important societal questions.
Okay.
Yeah, I think that actually the right group to ask that question to, while we can tell you scientifically, and statistically how trends are changing, that question is being asked every single day by businesses around this country. And I think that is where these are people who actually have to pay for the cost of what this changing world means. And they are incorporating this information, and they are looking to the future to understand how their risk is changing, not only to extreme events, but to average precipitation and average temperature trends, et cetera. And so while we can certainly tell you that, yes, things are changing and the past may no longer be the predictor of the future, what I think is really where the proof is in the pudding is the fact that businesses around this country are using this information to plan for their future, and that's because they also see these trends and these changes happening. And that's where I think that our science, not only within NOAA, but within the attribution community as a whole, that's what we are trying to do, is to provide that information so others can make more informed decisions about what the future might hold.
I think it's also interesting, if you look at the results in these papers closely, you might be kind of surprised if you weren't a climate scientist. Let's say you're a business person and you heard, temperatures have gone up a 1/10 of a degree or something, and globally you think, well, that's not a big deal. The reason to study extremes is you look at the changes in the odds of some of these extremes. We're talking about 5, 10 times, 100 times difference in the odds. Those are large changes because we're looking at the extremes, not just the norms. And so sometimes I look at these papers, I think, well, so there was a little effect. The little effects are big at this end of the curve. So they're very relevant pieces of information.
Okay, I think we have one more question from the chat. That'll be our last question.
Another question from Seth Borenstein at the AP. Seth asks, if you had to choose one 2015 event as the poster child for climate change-induced extreme events, which one would you choose and why?
You can go down the row if you want. Freddie, you want to go first? All right, I'll go first.
Yeah.
I'm actually going to choose our cover photo, which is the sunny day tidal flooding in Florida. We actually have the lead author here in the room. Billy Sweet is in the front row. And for me, I think this one is just very remarkable because truly, not a cloud in the sky. And these types of tidal and nuisance flooding events are clearly becoming more frequent. Billy was also the lead author on a paper in 2012 looking at the storm surge after Hurricane Sandy and showing that storm surge was also made measurably worse because of climate change. I think from the coastal community perspective, where a huge percentage of our population lives, this is something that they are going to be increasingly affected by. And so I think it's one that provided some great information about how their exposure risk might be changing.
I think I would actually choose, so there's one paper on the heat wave in India, because heat waves is the kind of thing where we think, oh yeah, we know how that goes. Heat waves are easy, heat waves are straightforward. But this paper, in that paper, that showed that although we know that heat waves on the global average are increasing, and that is due to anthropogenic climate change, we have the greenhouse gas signal, and we can disentangle this greenhouse gas signal. But especially in a lot of places in the world, we have actually sort of other factors that also influence the heat wave risk, and in particular the maximum daily temperatures. And over Southeast Asia, the aerosols that are also human-induced are playing an important role. And we are really facing very new and different challenges here in trying to disentangle these two effects and see what it means to the overall effect of heat waves. So I think there's also that's a great study on looking at what we have actually learned so far, and where are still open questions, and where we need to have better models as well, and where we need to put effort in to get better on disentangling these different anthropogenic effects.
Did I get a vote? I would never overrule Stephanie the lead, nor Jeff. But in the same spirit as Stephanie's choice is the dangers of the coastal margins. So the nuisance flooding is anything but a nuisance. I mean, it's just a big problem in coastal Florida. But I want to call out as a potential poster child of the future, and what it means to so much of society, where so many people live near the coastal margins, and where so many people are poor who don't have the mobility to get out of harm's way, where early warning is deficient compared to what we're used to in Europe and here in the United States. And that is the extreme behavior of cyclones in the warmest parts of the world oceans. We're not seeing this yet particularly, at least not that I'm aware of. We have experts in the audience that can address this with you in the tropical Atlantic hurricane season, which is of great consequence in the Caribbean and in the eastern seaboard and the Gulf of Mexico. But we are seeing much stronger evidence that changes are afoot in the cyclone behavior that invades into the Asian nations, where so many people are exposed, where the vast majority live in these low-lying areas, barely getting by subsistence living. And the concern on this is, if these storms are going to become more intense and more frequent, what is the recourse of the poor that live in these famished areas to begin with to evade the course of the storms that are coming their way and what will their future hold for them. So I really look at the typhoon study that was done by Zhang et al. As something to come back to and think about what the future world might look like if those are happening yet more often.
I'm not an extremist. Seems a funny thing to say here, but my limited experience with storm chasing taught me that what I actually like is just the atmosphere in general, the aesthetics of it somehow. What I was thinking when I was just reminding myself here, what I enjoy working on this, it's not so much to pick the worst or best extreme or whatever, but just to think about, in this issue in particular, we have some papers that have gone a step beyond. And I think Freddie's sort of alluding to that beyond of talking about impacts and simultaneously evaluating impacts and the extremes of the impacts as we evaluate the extremes and what anthropogenic climate change has done there. And I think we had a couple papers, I'm just remembering, that had to do with extreme drought in Western Canada, for instance, and the complexity of the issues there involved with the water supply and how drought is formed in that region of the world. It wasn't such a straightforward thing. I think we also had, we have wildfires in Alaska, right? And I thought that was a fascinating problem to ask. I mean, these are non-obvious questions. The obvious questions are often the heat wave stuff, but when people are getting into not just what was the heat, but what was the heat index? What did it feel like to people? Or in the case of the drought, where does the water go? It's not just a matter of snowpack, but there's some other questions involved. And in the case of the Alaska fires, convection and storms, and how are they changing, and can we get that into this question? Or is there a way to answer this question without getting into the weeds where we don't have modeling capabilities to answer the questions? Those are the papers that I like the most. So.
Okay, so that's all the time we have today, but thank you all for coming, and we'll resume at 1:45. Thank you.